Welcome back. In this video, we will prove that lines perpendicular to circle radii are tangent to the circle if they pass through the circle itself. If you haven't tried to prove this already, again, please stop the video and try to do it yourself. But let's begin now. To say things a bit more formally and to give things names, let's suppose that omega is a circle with center O. Let's suppose also that L is perpendicular to some radius OP of the circle, and that L passes through the point P. We will conclude that L is omega. The way that we'll do this, similar to the last video, is to proceed by a contradiction to give an RAA proof. So let's suppose that L is perpendicular to OP, but we'll suppose that it's not tangent to omega. Now since L does pass through the point P, it intersects the circle. Since L is not assumed to be tangent to the circle, that means that L has to intersect somewhere else as well, and we'll let Q be another point of intersection. Now, if we take a look at the segment PQ, by a previous theorem, we know that there should be a midpoint. Let's call that R. And by a theorem that we discussed last time in class, we know that the perpendicular bisector of PQ, which will pass through the point R, is guaranteed to pass through the center of the circle. So if we take a look at the segment OR, the segment OP, and the segment PR, we'll have the three sides of a triangle, and you can already see something a little bit strange about this triangle. The angles OPR and ORP are both right angles. Now that's a contradiction because in Euclidean geometry, the angles in a triangle should sum to 180 degrees. Now we already reach 180 degrees from these two angles, and that's not including any of the contribution from the angle centered at O. So we get a contradiction, and this tells us that the line L is in fact tangent to omega. All right, in the next video we'll prove our final theorem. We'll also be talking about another couple theorems that will be important. So tune in then, I'll see you there.